Good morning, students. In this session, we will discuss some important points in a brief manner from alkyl and aryl halides. See, when it comes to the preparation of alkyl halides, monohalides especially, one is the direct halogenation of alkanes. This we studied in hydrocarbons also. When alkanes are treated with halogen in presence of sunlight, a free radical mechanism follows, alkyl halide or alkyl chloride can be obtained. And here, alkyl free radicals will be formed, which gets joined to give alkyl free radical and chlorine free radical. In that way, the reaction follows free radical mechanism. When it comes to the action of hydrogen halide on alkenes, the second method, it follows Markovnikov addition rule, except for hydrogen bromide in presence of peroxide, organic peroxide, where it follows a peroxide effect or Karash effect or anti-Markovnikov addition rule will be followed. Otherwise, in all rest of the cases, in the addition of HX, Markovnikov addition rule only will be followed, and in some cases, even though mechanism is via Markovnikov addition, major product will be anti-Markovnikov. We will discuss that in the form of questions. And from alcohols, the next method of preparation, from alcohols we have first one, alcohols reaction with hydrogen halides, especially HCl in presence of ZnCl2, which is called as Lucas reagent. Okay, this reaction follows via stable carbocation intermediate. The mechanism is, first this OH will be hydrated, protonated. OH will be protonated because of this H plus, it becomes H2O plus, which acts as a good leaving group. And that good leaving group H2O will be absorbed by this anhydrous ZnCl2, leaving a stable carbocation. As a stable carbocation is associated, there are possibilities for hydride shift or aryl shift or methyl shift, and thus that stable carbocation will be attacked by X minus nucleophile later. Next, when it comes to the next method of preparation from alcohols, it is using phosphorus halides, trihalides or pentahalides, which also follows SN1 mechanism. So, these are the reaction skeleton. As PBr3 and PI3, PBr3, PI3 and bromine and iodine halides are unstable and they decompose readily, they should be prepared in situation. That is why instead of taking PBr3 and PI3 directly, sometimes in the equation you might have noticed that P plus Br2, P plus I2 will be given, because they will be prepared in situation, otherwise they decompose quickly. Next is Darjan's reaction. This is also from alcohols only. Like alcohol, this is also from alcohols only. See, it is alcohol when treated with thionyl chloride in presence of pyridine. Alcohol when treated with thionyl chloride in pyridine. Pyridine solvent in presence of pyridine solvent, it follows SN2 approach. SN2 approach means rare side attack will be followed. As a result of this, inversion of the configuration takes place. When SOCl2 is in presence of either solvent, it follows a new mechanism, a different mechanism called as SNI, nucleophilic substitution intramolecular mechanism, where in that same direction of the leaving group, suppose this OH will be the leaving group, right? In the same direction of the leaving group, OSO2 will be the SOCl will be the leaving group. In the same direction, even chlorine also will attack the carbocation. As it is in the same direction, intramolecular, within the molecule everything is getting disconnected and joined. It is called as nucleophilic substitution intramolecular mechanism, and as a result of this mechanism, there won't be any disturbance in the arrangement, stereochemical arrangement of these groups. That is why the same configuration will be retained here, that is called as retention. And when it comes to the next, alkyl bromide and iodide, as SOBr2 and SOI2 are not stable, we cannot use this method for the preparation of alkyl bromides and iodides. When it comes to Borodin-Hunsdike reaction, it is reaction of silver salts of carboxylic acid with the halogen in presence of CCl4 to give corresponding alkyl halide. And the next is halide exchange reaction. This is one of the important reaction actually. And here alkyl chloride or bromide will be treated with potassium iodide. Alkyl chloride or alkyl bromide will be treated with potassium iodide in presence of acetone to give corresponding alkyl iodide. You may get a doubt, why chloride is reacting with potassium iodide, why not chloride with KBr? If you do that, instead of Ki, if you take a KCl or KBr, here the problem is the KCl and KBr are more relatively more ionic in character. As they are more ionic, they are not available in dissolved state in acetone. They settle down as precipitate. As when they are not available in the reaction medium, how can they react with? That is why this is suitable only for iodide, and this particular reaction is called as Pinnacle-Steins reaction. And when it comes to the another reaction, that halide exchange reaction, alkyl chloride when reacts with the fluorides of mercury, cobalt, antimony, etc., corresponding alkyl fluoride can be obtained. This is called a Schwarz reaction. It is just a recap of the reactions. We all studied all these things. And alkanes when reacts with sulfuryl chloride, that is thionyl chloride, somewhere we studied Darjan's reaction. This is thionyl chloride, this is sulfuryl chloride in presence of sunlight and organic peroxide, they give the corresponding alkyl chloride. When it comes to the allylic halogenating agents, like you know the meaning of allyl carbon. Allyl carbon means sp3 hybridized carbon next to sp2 carbon, sp3 hybridized carbon next to sp2 carbon. This is sp2 carbon next to sp3 hybridized carbon. This is sp2 carbon next to sp3. So, these two carbons can be taken as allyl carbons, right. And allylic halogenating agents are this one, N-bromosuccinamide, sulfuryl chloride, and even chlorine at high temperature also can be taken as allylic halogenation, chlorine at high temperatures. So, with respect to the condition on the arrow, one can easily assess whether it is normal halogenation or allylic halogenation. So, this is about allylic halogenation reaction. See, allyl position is halogenated in these two cases. Next, when it comes to the preparation of aryl halides, means chlorobenzene or halobenzene, etc., benzene on direct chlorination in presence of Lewis acid. Here another question possibly is, what is the purpose of taking Lewis acid? Everyone will remember Lewis acid, FeCl3 or AlCl3, etc. But what is the purpose of Lewis acid? The purpose of Lewis acid is to generate halonium ion as electrophile, to generate Cl plus electrophile. That electrophilic substitution, it is aromatic electrophilic substitution, right. To generate that electrophile, we need a Lewis acid. And another method for preparation of halobenzene or Sandmeyer's reaction, where benzene diazonium chloride, see the position of positive charge also. Benzene diazonium chloride when reacts with cuprous halides in presence of HCl gives the corresponding halobenzene, and similarly with the cuprous cyanide in HCN gives the corresponding cyanobenzene. A similar reaction was the Gattermann reaction, where benzene diazonium chloride reacts with copper and HCl to give chlorobenzene, copper and HBr to give bromobenzene, okay, copper and HCN to give cyanobenzene, etc. And one more reaction is Ball-Scheiman reaction. Well, like we have a specific reaction for iodoalkanes, that is the Finkelstein's reaction. For fluoroalkanes, we have Schwarz reaction. The same way, for fluorobenzene, this is a specific reaction, Ball-Scheiman reaction, where HBF4 will be used. And when it comes to the physical properties of these substances, dipole moment is one of the important area. Usually dipole moment, it depends on polarity. More the electronegativity difference, more is the polarity. We are all aware of that point. So, one expect methyl fluoride to have more dipole moment than methyl chloride, but practically it was observed as chloride is of more dipole moment than fluoride. Why? What is the reason? Actually, dipole moment is a product of charge and distance between the two poles. Charge and distance between the two poles. As this product is dominating for chloromethane, dipole moment of methyl chloride is greater than that of methyl fluoride, and the rest sequence is as usual. And one more question possible is dipole moment of methyl chloride, dichloromethane means methylene chloride, chloroform and carbon tetrachloride. So, how to remember all these things means one shortcut we can generate with increase in number of halogens, dipole moment decreases. See, as the number of halogens are increasing, dipole moment is decreasing, and CCl4 had reached 0 dipole moment, right. When it comes to the chemical properties of these alkyl halides, they are more prone to show nucleophilic substitution reactions because of the polar carbon halogen bond. You are aware of that. Now, that halogen should be replaced by another nucleophile, for which halogen should be a good leaving group. Not only for this compound, for any such substitution reactions, nucleophilic substitution reactions, the eliminating group or leaving group concept is very important. It plays a major role. Okay. So, leaving group ability is inversely proportional to basic character. leaving group ability is inversely proportional to basic character. Weak conjugate base acts as a good leaving group. That's the line. Weak conjugate base acts as a good leaving group. Like if it is weak, after going out, after getting eliminated also as it is weak, it won't react much. Means it is stable. In that way, a weak conjugate base acts as a good leaving group. This is the decreasing leaving group ability of some groups. Better you remember. Decreasing leaving group ability of some groups. So, depending on their leaving group ability, we can answer some questions. And when it comes to the SN1 mechanism, nucleophilic substitution mechanism, SN1 is there, SN2 and SNI in our syllabus, right? SN1 mechanism, it is nucleophilic substitution unimolecular, means rate of this reaction depends on concentration of only substrate. That is why first order reaction. So, that one corresponds to unimolecular and first order also. It takes place in two steps as usual. The first step is formation of a stable carbocation intermediate. Like this alkyl halide, bond gets weakened, which is a transition state actually, and in a slow step, which is also called as the rate determining step, halogen leaves the site as by heterolytic cleavage as X minus, generating a stable carbocation. As we discussed earlier, whenever a stable carbocation intermediate is associated, there are possible hydride, aryl and alkyl shift with respect to electron density. Right here also, stable carbocation intermediate is possible. So, this is the potential energy diagram. See, reactant or alkyl halide, it is reaching a transition state 1 and is generating a stable carbocation intermediate. This corresponds to carbocation intermediate, this corresponds to transition state, and this is step 1. And in step 2, this was attacked by a nucleophile. See, carbocation is getting attacked by a nucleophile in a first step, where a partial bond between nucleophile and carbocation takes place in a transition state again, second transition state, and that from that transition state in a fast manner, bond between carbon and nucleophile will be generated. So, in this way, the question on these graphs are also possible. Number of transition states possible, 2 transition state. Number of intermediates possible, 1 intermediate, stable carbocation intermediate. Now, let us see factors influencing SN1 reactivity. So, nature of substrate SN1, as it is a stable carbocation intermediate generated. So, tertiary alkyl halides are more reactive than secondary, than primary, than methyl halides, right. So, in this way, nature of substrate can be explained. And the second factor that influences SN1 reactivity is good leaving group, like I minus is a good leaving group than Br minus, than Cl minus, than F minus, because their conjugate acids, if you take HF, HCl, HBr, HI, HF is a weak acid, so F minus is strong conjugate base. HI is a strong acid, so I minus is a weak conjugate base. As we discussed now, weak conjugate base acts as a good leaving group, that is why in this way. F minus also acts as a better leaving group in polar aprotic solvents. Polar aprotic means which do not generate any proton. And when it comes to the third factor, presence of unsaturation at alpha carbon. Presence of unsaturation at alpha carbon decreases SN1 reactivity. So, this is the carbon to which functional group is connected is alpha carbon. At alpha carbon, unsaturation is there. In case if this is to be subjected for nucleophilic substitution, see what is happening due to the polarity of this pi bond, there is a partial double bond formed between chlorine and this carbon. Due to the partial double bond character, bond gets strengthened and it will not dissociate with expected ease. So, it is less reactive. In that way, as a stable carbocation cannot be formed, it is less prone for SN1 reactivity. So, thus presence of unsaturation at alpha carbon decreases SN1 reactivity. And when it comes to the next factor, presence of unsaturation on beta carbon. So, this is alpha carbon, this is beta carbon, increases SN1 reactivity. How? When chlorine leaves the site, this will be carbocation, which is called as allyl carbocation, that can be stabilized by delocalization of pi bonds, right. So, because of conjugation, see, this allyl carbocation can be stabilized well, and that is why presence of unsaturation at beta carbon increases SN1 reactivity. And the next factor is heteroatom with lone pair. Presence of heteroatom with lone pair on alpha carbon. Presence of heteroatom with lone pair on alpha carbon. This is alpha, and which is followed with a heteroatom with lone pair. What happens here when this chlorine leaves the site, CH2 bears a positive charge, that is a carbocation. It is immediately getting stabilized by mesomeric effect of this heteroatom having lone pair. See, in that way carbocation can be readily stabilized. So, because of this point we can say heteroatom with lone pair on alpha carbon increases the stability of carbocation, so increases the SN1 reactivity of the corresponding halogen. And because of the same reason, ROCH2Cl is said to be more reactive towards SN1 than normal aliphatic alkyl chloride. Next favorable factor is heteroatom with next factor that affects SN1 is heteroatom with lone pair on beta carbon. Heteroatom with lone pair on beta carbon, this is beta, this is alpha. Heteroatom with lone pair on beta carbon, when Cl leaves the site, this is a C plus carbocation is formed. Now at this moment this oxygen shows only minus I, there is no scope of showing its plus M mesomeric effect. That is why only minus I will be shown in a more pronounced manner, which destabilize the carbocation. Thus, presence of heteroatom with lone pair on beta position decreases SN1 reactivity. And when it comes to presence of electron withdrawing group on alpha carbon, it decreases SN1 reactivity. Presence of electron withdrawing group, see, carbocation is generated. Because of withdrawing nature, carbocation will become unstable. In that way, electron withdrawing group at alpha also decreases SN1 reactivity. And when it comes to the next point, concentration of nucleophile do not play any major role, because the rate is independent of concentration of nucleophile. It depends only on concentration of alkyl halide or substrate. It is independent of nucleophile. And next point is solvent. As this carbocation should be stable in this reaction, in this mechanism. So, to get to surround that and to stabilize the carbocation, we need polar protic solvents. Polar protic solvents increases SN1 reactivity. Now, let us discuss some questions on these chemical properties of alkyl halides. What is the major product of the following reaction? So, this is a secondary alkyl halide given in presence of tertiary beta oxide and tertiary beta alcohol. So, this condition stands for alcoholic potash, right? Alcoholic KOH. These two conditions indicates that this is alcoholic KOH. Alcoholic KOH is what type of reagent? It is a dehydrohalogenating agent. Dehydrohalogenation means it removes halogen from the alpha carbon and hydrogen from its beta position. Beta means this is beta, this is also beta. Now at this point we need to concentrate at one area. See, because of this base, tertiary beta oxide base, it follows a fast single step mechanism, right? That is it follows E2 mechanism. E2 mechanism means in the same step elimination of leaving group and removal of beta proton takes place simultaneously. Just now we discussed in the mechanism. E2 mechanism means it takes place in single step. E2 mechanism takes place in single step in which elimination of leaving group and removal of beta proton, elimination of leaving group and removal of beta proton, this proton or this proton, whatever it is, see, takes place. That is the first point we need to concentrate. Elimination of leaving group and removal of beta proton either from this beta or from this beta. Next point we have to concentrate is this E2 elimination is always anti-elimination. E2 elimination is always anti-elimination, means what? The direction in which leaving group is moving out, in its opposite direction proton will be removed always. Leaving group and proton, this is methyl actually, it is not specified because it is a bond line notation, that is methyl. Leaving group and the beta proton should leave in opposite direction. Leaving group and beta proton should move out in opposite directions. Understood? So, this chlorine direction is C, it is given with a dash, whereas it is given with this symbol. So, these two are in opposite direction. This is alpha carbon, this is beta. In its opposite direction, methyl is there, not hydrogen. So, where opposite direction methyl is there, here we can take hydrogen, see. So, opposite to the direction of leaving group, beta proton is there at this carbon, not at that carbon. Suppose this is beta dash. So, instead of beta proton removal, here also proton is there, but the direction of proton is same as that of leaving group. But for E2 elimination, it is anti-elimination, right. So, leaving proton should be in the opposite direction of the leaving group. So, this hydrogen and this halogen will be eliminated, giving a unsaturation at this junction. So, this is the answer, because in all the remaining cases the product is differently given. Next, when it comes to this question, order of rate of reaction with AgNO3 or rate of SN1 reaction. So, its rate will be more when its intermediate formed is more stable. More rate will be shown when the more stable carbocation intermediate is formed. Like suppose when this is the first compound considered on leaving group elimination, it had given, see, a compound, this is aromatic. What are the conditions for aromaticity? Planar structure, conjugation of pi with another pi or lone pair or with a positive charge, 4n plus 2 number of pi electrons. So, it is following all those rules, and when this is stable, and when it comes to this next molecule, this on elimination of leaving group had formed cyclic propylium ion, cyclic carbocation. See, this is also stable because of this is called as dancing resonance structure, we can discuss. And when it comes to this third molecule, this is the carbocation formed with the elimination of leaving group. In this carbocation, it is planar of course, but it is said to be following 4n number of pi electrons, 4n rule, which is for anti-aromaticity. So, anti-aromatic is less stable, no. So, among aromatic and that anti-aromatic, aromatic is less stable. So, as the stability of this first carbocation is greater than second, greater than third, one is said to be more reactive. Therefore, reactivity of 1 is said to be greater than 2, greater than 3. So, 1 greater than 2 greater than 3 means which option? Option C. Another question from nucleophilic substitution mechanisms. See, free energy profile for the given reaction is given. OH minus is the nucleophile attacking methyl bromide and methyl alcohol is generated with Br minus. The approach here itself we can say OH minus is attacking from the rare side. So, it is an SN2 approach. SN2 approach takes place in one step, rare side attack, where inversion is also possible if it is a chiral carbon. Of course, all the points must be recapped once. Now, there is no intermediate formed here, everything takes place, elimination of leaving group and attack from the rare side by nucleophile takes place in one single step. One single step means it should be via transition state, not intermediate transition. There is no transition state here, and this is a transition state. These three are associated with the transition. And as deciding thing is, as it is a spontaneous process, Gibbs energy should come down, delta G should be negative. So, for this it is 0, there is no equilibrium given. For this it is positive, for this it is negative. So, answer is B. This is D option, this is option C, this is option A. Answer is second option. Right. Now, when it comes to the next question, in the given reaction, thioether, alpha beta, beta bromo thio diethyl ether, that is the name. When subjected to hydrolysis, X is formed. What is X? So, here there is an asterisk on this carbon, you have to notice such points. Now, usually immediately one will expect bromine get replaced by OH like that, but there is a small mechanism even for this also. Let us see that mechanism. CH3, CH2S, CH2 star, CH2Br, as it is a good leaving group, when it leaves the site, CH3, CH2S, CH2 star, CH2 plus. Now, this is a heteroatom with lone pair at beta position, heteroatom with lone pair at beta position. So, stable carbocation intermediate will be favored due to this heteroatom with lone pair at on beta carbon. So, there is a dative bond formed between these two. So, as a result of this, CH3, CH2S, CH2 with asterisk and CH2. Now, plus charge is on sulfur. This is an intermediate formed. Now, this will be attacked by H2O actually. That will be actually attacked by H2O. H2O can attack at either of these two carbons, because as it is symmetric in all aspects, it can attack on this carbon or it can attack on this carbon. Then as a result of this, so H2O will attack and H plus deprotonation takes place, OH will be left. OH will be left either on this starred carbon or on this non-starred carbon. So, this product and other product both are possible, both the product are possible. Then both A and B will be formed in 1:1 ratio, because in either way the attack may takes place. In either way attack may takes place. That is why OH may be at this carbon, then this will be the product. OH may be left on this carbon, when the bond break, then that will be the product. So, 1:1 mixture of A and B is the answer. This is another question from dehalogenation of the given dibromide. When this dibromide is subjected to dehalogenation, which is the product or major product, like that, that is the question. Now, you see, we have to convert this into Fischer projection in this way. So, we have to assume that these two like groups or main groups should be parallel to one another. We have to rotate that in such a way. So, when it is rotated by 180 degrees, this is rotated by 180 and 180, this is what the projection. And when you project this, when you look at this molecule upward direction or in this way, in this direction, if you look at the molecule, methyl carbon carbon methyl, methyl carbon carbon methyl. So, vertical carbon chain, the top and bottom groups are projected behind the board. That is the rule in Fischer projection, and these H and Br are projected towards the observer. So, in that way we can say that the given molecule is a meso compound. Like this, once if you get that meso structure or non-meso, then we can use a shortcut. If the terminals are same, and is a meso, if the terminals are same, then eliminating groups are on same side, means meso. Eliminating groups are on same side, then the obtained product will be trans product, trans alkene. If the eliminating groups are on opposite side, then the obtained alkene will be cis alkene. So, this is another shortcut we can follow. To save the time. This is terminal groups are same, eliminating groups are on the same side, means meso, same side means meso, right. Then in such a case by E2 elimination, it gives a trans alkene, like this. Where is trans alkene among the 4 options? Suppose if this is the plane containing the double bond, then for this double bond methyl is above and one methyl is below. So, this is a trans alkene. Whereas, for this plane containing the pi bond and saturation, both the methyls are one side of the pi bond. So, it is a cis alkene. So, answer is trans alkene. This is another question from dehydration of alcohols. When the given substance is subjected to dehydration using an acid catalyst, what will be the product possible? Here what happens, immediately when that substance is subjected to dehydration, so it become OH2 plus along with this cycle given at the para position. See, it is a 5 carbon cycle. Now, this acts as a good leaving group, leaving a positive charge here, and a cycle will be formed. Cycle is as it is. Now, what happens? There is a scope of ring expansion. In this, right. So, what happens here? Because of resonance, we can study resonance here, right here. So, this bond will be polarized, you can take it. Now, as this is positive charge, by means of resonance, so here positive charge will be obtained. See, now as a result of this, there is a ring expansion, like this dissociation takes place and ring expansion is possible. As a result of this, a positive charge will be left at this carbon. This, whatever the bond polarity happened, because of that positive charge is left. Now, whenever a reaction is initiated by protonation, see, whenever a reaction is initiated by protonation, definitely it will be terminated by deprotonation. So, minus H plus using a base. Using a base, whatever the base left here, it removes a proton from this carbon. When H plus is removed, C minus will form a pi bond with this. So, this is the compound form. So, it belongs to which option? This bicyclic compound belongs to first option. Another question. When C3H7I treated with alcoholic KOH, it had given some compound X, which on further reaction with N-bromosuccinimide. You have to recap, N-bromosuccinimide is for allylic halogenation. On allylic bromination, it gives Y. Y on reaction with alcoholic KCN had given Z. Okay, that is another substitution. Now, C3H7 means in a 3 carbon chain, wherever halogen is there, it may be on first carbon or it may be on second carbon, whatever the arrangement or structure, alcoholic KOH. Alcoholic KOH is a dehydrohalogenating agent and hydrogen halide and hydrogen halide. In either way, it gives CH3, CH double bond, CH2. Propene will be the product X. This is X. Now, this X is subjected to allylic halogenation in presence of N-bromosuccinimide. We already discussed in the few minutes before. N-bromosuccinimide, sulfuryl chloride, SO2Cl2 in presence of sunlight and halogen in presence of high temperature. Halogens also at high temperature, they leads to allylic halogenation. So, N-bromosuccinimide means allylic bromide or allyl bromide will be the product. Now, this allyl bromide is subjected to nucleophilic substitution using alcoholic KCN, where Cn minus replaces bromide. The product will be CH2Cn, CH double bond, CH2. Now, what is the product relevant option? This one, option C. See, another question from this aryl halides. When all 6 isomer of C6H6Cl6 means 1, 2, 3, 4, 5, 6 hexachlorocyclohexane, okay, is heated with alcoholic KOH, most probable product is, nice question it is actually, C6H6Cl6 means C6H6Cl6 can exist in 2 ways. One is all chlorines are in cis form and alternate cis form. Alternate cis form means one chlorine is above the plane, another chlorine is below the plane. In case of all chlorines in cis position, here we need to start with the E2 elimination mechanism. As E2 is anti-elimination. What's meant by anti-elimination? If chlorine is removing in one direction, beta proton will be in another direction. And if all chlorines are in cis form, then alternate chlorine and alternate hydrogen will be eliminated. So, elimination is possible. E2 elimination is possible in this case. In case of alternate cis means alternate chlorines. Alternate chlorines means one chlorine is above and again third carbon chlorine is above, like that. Second carbon chlorine is below the plane in that way. Then E2 elimination is not possible. So, E2 elimination is not possible in case of alternate chlorines above and below the plane. When all